Good morning, everyone. Many thanks for coming to the Trevor's PhD defense. Just a little bit about Trevor. So he started his PhD as soon as I actually joined UNT September 21, right? At that time, my lab was not ready. It was just space, but immediately he started his work. I'm very, perhaps I should not say at the beginning of the presentation, but I'm very impressed by his work, and having Trevor in my lab felt like I have a couple of PhD students in my lab. So like he was multitasking, doing so many things. But Trevor has been working on my NSF career award as on thermoactive soft actuation, but at the same time he was working on another topic, which he will explain later, is thermo-responsive variable stiffness actuator. So basically, one of them should be a topic for a PhD dissertation. He has done it two, so actually consider it like a 2 PhD dissertation. So like, if I compare it with my PhD, it's like double. So he's been working on that project and been mentoring so many master students and TAMS students and helping me with whatever we have in the lab. So without further ado, I'm gonna ask Trevor to start his PhD dissertation defense, and then after that, we're gonna have Q&A session, right?
Yes.
Thank you.
All right, great. Thank you all for being here today. What if I told you that the tools for enabling the next generation of robotics you already have? They're just located in your kitchen. Today, like Dr. Jafari said, I'm going to be talking to you about the research I've been doing the last 3 years on phase change actuators for enabling the next generation of physical human-robot interaction. So when you think about a robot, maybe you think things from pop culture such as like WALL-E. When I think of a robot, traditionally I think of an assembly line, maybe these huge robotic arms putting together cars with very precise motions. And with this, you'll notice something about this image, and it's that there's no humans in there. Maybe there's a human taking the picture, but really the only time humans get close to these robots are when they're turned off and maybe just performing maintenance. The problem with these that make them unsafe for humans to be around lies in this, a motor. Or more specifically, what we attach to a motor in a gearbox. What this does is that engineers have made motors that are able to spin really fast, and that's great, but sometimes we need extra strength. These gearboxes trade off that speed and increased torque. Something else they do, though, is they add in this concept of reflected inertia. And this reflected inertia, or resistance to change in motion, is what makes these robots dangerous. For example, let's say we have a pinwheel, and I'm blowing on this pinwheel, and it's spinning. I have no problem sticking my finger out and stopping the blades without getting hurt. If I had a gearbox attached to it with a motor, let's say I have a gear ratio of 10. Not only would it slow it down by a factor of 10, it would increase the torque by a factor of 10, but this reflected inertia, it would increase by 100. So now when I'm sticking my finger out, I'm not feeling this pinwheel, I'm feeling something more along the lines of this. And that's where, regardless of size, these gearboxes can make traditional robotics very dangerous for humans to be around. So what options do we have? Well, we have two options, and I'll talk about both today. On one side, we can say, okay, forget the motors, forget the gearboxes. Let's see if we can create soft components that can accomplish these same motions. On the other hand, we can say, okay, well, maybe the gearboxes and motors aren't so bad, but let's just get rid of that reflected inertia, make these devices safer for humans to be around. So starting off on that first aim, when I say soft robotics, it's exactly what it sounds like. It's these robotic platforms that we create that are completely soft. And something that you can ask yourself throughout this presentation is one aim better than the other? should we be moving all traditional motors over to soft? Or should we really just keep on relying on these traditional motors? Each of them have benefits and each of them have drawbacks. And something going into the future that we'll find is that there really is going to be cooperation between these two different areas. Traditional actuators, robots, are really good at precise movements, handling large payloads. However, as seen in the image, soft robotics might have more of a delicate touch, might be able to respond to the environment even if the environment's unknown. So I'm sure you've seen some examples of soft robotics in pop culture from around 2014 when Big Hero 6 introduced the idea of Baymax, a completely soft robot that is capable of interacting with humans, or even in 2018 when there was a new spin on Dr. Octopus using completely soft tentacles. With these, they are soft materials such as silicone elastomers, and they have similar mechanical properties as our tissue and skin with our bodies. So it comes back to those two aims. We have two solutions that I'll talk about today. The first is that we can create soft muscles that are able to accomplish similar motions that we might be able to achieve with our human skeletal muscles. On the other side, we want to also look at how we can change the traditional actuators and give them compliance to have compliant joints. To start off, there are a lot of different stimuli for controlling soft robotics. The most popular is probably pneumatic. And what this is essentially taking soft materials and introducing some cavities with them, and then applying pressure to the system to achieve different deformations. In this, you see this inflatable cavity, and due to the way that the geometry is in the cavity, it creates a bending motion when pressure is applied. With this, you'll notice that there's this huge air supply system, which is very heavy and very loud, which is detrimental when you're looking at soft robotics interacting with humans. Let's say you have these kinds of soft robotics with a prosthetic or a wearable or assistive device. You don't want to lug around a huge air tank and compressor system, so that's a big drawback. Other stimuli have also been introduced and researched, such as electromagnetism, where essentially you have to use big external magnets, such as an MRI machine, and then have that magnetic field interact with a magnetic field generated by your materials. Or maybe you introduce a current to a soft material and generate a magnetic field like that. That interaction is what causes the motion in this case, and I'm sure, as you guessed, no one's really willing to lug around an MRI machine or a large external magnet for having these in these wearable robotics. There's even newer versions that are discovered by universities such as University of Colorado Boulder, which looks at the Hazel dielectric soft actuator. And this you can think of as just essentially a Ziploc bag with some vegetable oil in it. And by applying a very large voltage, you are able to get complex deformations, essentially have it act very similar to human skeletal muscles. Now with this, when I say a large amount of voltage, I mean a lot. We're talking on the scale of 20 to 30 kilovolts, which again is not very feasible when it comes to having these systems applied in these wearable and rehabilitative devices. And then finally, we come to the area that I will be talking mostly about today, the heat or thermal domain. With heat, they have found ways to introduce materials that are completely soft, that are responsive to a heating stimulus. And with this, I'll get into a lot of the benefits and drawbacks of them as we go along, but the main drawback is that they're very slow. And we can see here that really none of these solutions yet have seen widespread implementation because of those drawbacks that they have, whether it's lack of portability, difficulty of manufacturing, speed or efficiency. So that brings us to my first aim today in Teresa, thermally reversible soft actuators. So back in 2017, Miriam et al. Came up with a design to where you can cure silicone, but while you're curing, you actually introduce a phase change fluid, such as ethanol. And when you have it cured like this, you essentially create these microcavities that you see here on the right. What these microcavities have in them is essentially it's a mesh of silicone with this phase change fluid in these little holes. And then whenever you bring the temperature above that vaporization temperature for the phase change fluid, you get this total volume expansion. And with that, initially for heating, we use a principle such as joule heating, which is essentially just having a wire go throughout the entire silicone body, and then by applying a current to that wire, you have a temperature change, an increase in temperature, using the current squared times the resistance. Now, here, we can actually watch what they did in 2017. You can see they're able to have this silicone composite that as they apply that joule heating, they get sort of this breathing motion, this motion very similar to human skeletal muscles. Now, something to note here is this X16 in the bottom right. This is actually sped up 16 times fast. Now, I don't know how this guy holds his hand so still for that amount of time, but it's very impressive. However, the technology itself is kind of lackluster, right? You're using this simple mechanism of phase change fluid, but it's so slow. And notice how I only said joule heating. I didn't talk anything about cooling. And that's because we can only actively heat using this mechanism. And then when it comes to deactuating or relaxing, we rely on the ambient temperature. So what they did after that is they said, okay, well, let's take this technology and let's implement it in a human skeletal application, where they have two of these devices, one as a bicep and one as a tricep. Now, as I put this on the left, what you'll notice is they have it to where whenever they cause the flexion, they're just contracting the bicep and the tricep is completely relaxed. Now, when it comes to actually relaxing after that, normally as humans, we would contract our tricep while relaxing our bicep. Here, the difference between these two is, again, we don't have active cooling. So on the right side, you'll see they deactuate by doing the same as humans, contracting the tricep. On the right side, however, or on the left side, however, you will see that they're just deactuating by unplugging the system and having the ambient cooling take over. So the difference in that case is 4 minutes for that full process by using actuation, the joule heating, versus, I could still be talking for a couple more seconds. This is going to take 7 minutes for full process when you rely on that passive cooling due to the ambient temperature. So clearly, something needs to be improved. We cannot have this slow speed when it comes to implementing this technology in actual applications. So what I propose in my research is implementing a thermoelectric cooler, or a Peltier device. What this is instead of using joule heating, this we can think of as a plate where whenever you apply a current to it, one side gets hot while the other side gets cold. The great thing about this is if you were to reverse the direction of the current, the side that was hot now gets cold and vice versa. So this has feasibility of actually implementing active cooling so that hopefully we can speed up the actuation process as well as have reversibility. Now when it comes to the cooling and heating versus joule heating, we actually have 3 terms. The first term is the reversible process, and that's actually a function of the current, the temperature, as well as the material properties of the device. The second term you might see is a little familiar. We actually still have joule heating associated in the device, because as we apply a current, it will just gradually heat up. That's its nature. And then finally, because we have this heating junction where we have a different temperature on each side, those temperatures actually affect each other. We have thermal conductance, to where as the temperature, as this device is on longer, the entire temperature of both sides will gradually increase, which is a drawback. Now, we look at research that's out there, and there's actually people that have implemented this in these sort of soft actuators with phase change material, where you can lift up a penny by heating up a pouch filled with the phase change material. Something you'll notice with this, though, is they take advantage of one side of the Peltier and reversing the current to have active heating and cooling, but the other side is just sitting there. They're not using it at all, which effectively makes it a very inefficient system. So then I go from here and say, okay, well, they can actually create these devices, these Peltiers, that are completely flexible. And hopefully by using the completely flexible Peltiers, we can implement them to create these completely soft artificial muscles for different applications. And hopefully close some of that gap from where we are now to actually having these devices implemented in wearable technology. So when it comes to joule heating, you'll notice that, again, we can heat it very well, but after getting to that point of heating, we rely on that ambient cooling, which is why it's very asymmetric having this long process of returning back to room temperature. Whereas with Peltiers, we can bring some symmetry to that, to where the heating and cooling process become very similar in the amount of time they take. So we took from where Miriam was, and we said, okay, let's replace the joule heating with these Peltier. And what we found with that is by curing a small cylindrical sample using their process, we get pretty symmetrical actuation of lifting this piston up and down over time. With this, it is still a very slow process, with lifting it 3 times taking about 6 minutes. So from there, we say, okay, well, clearly there must be some considerations that are new now that we're not using joule heating. So we took their device again, this silicone composite filled with a phase change fluid, and we heated it up using a Peltier. And I didn't just put the same image up there twice. This is after 50 seconds of heating. You can see there's really no difference. Actually, what we see is that there's a lot of bubble formation at the surface rather than a gradual total volume expansion. Okay, well, this is probably due to the fact that joule heating is able to uniformly heat the entire body of the silicone, where with this, we're only heating from one surface. So let's scrap the microcavities and look at just one large cavity. Well, by doing this and injecting fluid inside, we see an increase in expansion in even less time. But here, we still have that layer of silicone between the heating surface and the phase change fluid. So taking it a step further, we can actually embed the Peltier to where the fluid is just resting on its surface and get improved results with both actuation and time. With this, we see that now there are many other things that we have to begin to consider when it comes to applying this technology. With that, I mean, coming back to joule heating versus this new planar heating, think about, for this case that I showed you, gravity helps us out. We're able to heat, and it doesn't take a lot of time for the temperature to reach that phase change fluid. But what happens in another case, where maybe we heat from a different surface where the liquid isn't cooling? Well, then it becomes very slow to where maybe it's even more inefficient than the joule heating previous, and we're not really able to take advantage of the Peltier reversible heating and cooling. So with this, we decided to, since gravity now plays a role, we decided to move away from silicone elastomers. So let's go away from what was previously done with having that silicone curing process, and instead let's look for a material that is capable of eliminating the effects of gravity, still being heated by the planar heating of the Peltier, as well as maintaining a seal around the fluid. And we found that in the kitchen with vacuum sealed bags or Mylar bags. Now, with this, there's previous research that looks into this concept of pouch motors, of having these thin, flexible, but not stretchable materials that can be pumped up with air. And even past that, people have looked at incorporating phase change fluid into them and having it to where now, again, you don't have a stretchable material, but you have a purely flexible material that you can cause volume expansion in based on the phase change fluid. The great thing with this is that we can incorporate it pretty easily. We can essentially buy Mylar bags, seal them, and then inject the fluid inside. And with this, we get a relatively quick phase change process, around 15 seconds compared to the minutes it took before, with a very uniform or symmetric heating and cooling cycle, or actuation and deactuation. With this as well, now that we're not working with stretchable materials, we have to reconsider what the manufacturing process is. Well, like I said, we can buy Mylar bags, essentially bags that have aluminum coating on the outside, while they have polyethylene on the inside. And that polyethylene, whenever you heat it up and apply pressure, you can actually heat seal it and create these new seals. So we cut to a desired size, we apply the pressure and heat, and then we're able to inject the fluid before completely sealing our pouches. And by doing this, we can then geometrically model the pouch motors and figure out how much fluid should be injected. And we can do this because now we're no longer working with non-linear stretchable materials, we're working with predictable, flexible materials that we can model using simplistic geometry. So with this, we were able to create a model that allows us to figure out the optimal amount of phase change fluid to input into the system, as well as even build off of that into series pouch motors, to where we can take into consideration any kind of channels or number of cavities that we have in the entire muscle or pouch motor. Now, what we are trying to validate with this is if we really can use this technology to eliminate these effects of gravity, to increase the thermal efficiency, taking away from the silicone, increase the fluid retention, as well as now using this geometric model, optimizing the amount of fluid that goes inside. So with this, this is a video of two of the pouches on each side of a Peltier, and we see that we have a relatively fast reversible process for moving back and forth. Now, this is something we did to validate this process to ensure that we were able to get some kind of actuation from the same phase change principle. From here, we looked at typical applications that you would find in any kind of robotics paper. Typically, in the field of robotics, you look at making applications that resemble human skeletal muscles, that allow you to analyze manipulation, as well as locomotion. And we looked at all of these, and something we're doing that's completely new is taking advantage of both sides of the Peltier. Previous applications look at only applying the heating and cooling from one side of the Peltier, but we believe that by using both sides, you can have these devices that are much more efficient and able to achieve these complex motions as opposed to others from before. So with the muscle, we have flexion by applying heat in the direction of the bicep, and then we have extension that returns to the initial position by applying heat to the tricep. Now with this, what we find is that as the current goes through these devices for a longer period of time, the total temperature of the Peltier increases. So the flexion ends up being a significant angle change, but then when it comes to the extension, even though you have expansion of the tricep, it doesn't quite come back to that equilibrium point. And that's due to the Joule heating and thermal conductance that we saw earlier in the equation for getting the heat from the Peltier. So as current goes through the device for a longer period of time, the thermal management isn't very good. And that allows for a lot less control as time goes on. And what we'll find with some of the other applications is that the device needs some time to sort of breathe or cool off in between actuation cycles. So for a gripper, we look at grabbing an inorganic shape, and by doing this, this is just a piece of a sponge. We have control over flexion to grab, as well as we can let go by reversing the current and actuating the pouches that are on the outside. Looking something like this, to where we have this reversible process for picking up and letting go, as well as we can also grab using the extension. So having it to where we actually put our gripper inside an object and have it actuate the other direction to grab from the inside, and then you can imagine as you flex, you are able to let go of objects. So with this, we find that this sort of agonist-antagonist design, this using a pouch on both sides of the Peltier, allows for a lot of control over the actuation and over manipulating these different objects, as well as taking inspiration from human skeletal muscles in the bicep and tricep configuration. Now finally, we look at locomotion, how we can actually make a crawler that is able to move forward. And something I'll point out with this again is that you'll notice periods where it's taking steps forward, and then you'll notice periods where it has to sort of sit there for a while. So it's still a relatively slow process in achieving locomotion, but by using this reversible, flexible Peltier, you are able to have motions that you cannot previously achieve with Joule heating. And with this, since you are causing a phase change on both sides, you can then transfer the heat from one to the other as time goes on. Now, we talked earlier about wanting to eliminate the effects of gravity. Well, when it comes to locomotion, what you'll notice is that we have this sort of flat shape for our Peltier, and we have a pouch on top and a pouch on bottom. Well, the pouch on top, the liquid pools on the Peltier. On the bottom, the liquid is pooling away from the Peltier. And in the video that you saw previously, there was no sacrifice in the performance when it came to the effects of gravity, when it came to the flexion versus the extension in activating the two modules that we have attached to the Peltier. So from here, this is applications that we looked at for the muscle side. And now what we want to look at is for the second project, looking at how we can use these thermoactive phase change materials for variable impedance actuators. And this is more looking at the level of a joint rather than the level of a muscle. So first we can ask ourselves, what is impedance? Well, impedance consists of stiffness, damping, and inertia, and all of these components are characteristics of what we are looking for in a joint. We're looking for some sort of compliance. We're looking at compliance related to the elastic components and the stiffness, the viscous components and the damping, as well as the mass or inertial components and the inertia. So initially, again, we're going back to the motor and the gearbox. So traditionally you have this middle term with a gearbox that is associated with a reflected inertia. This is what we're trying to eliminate. And back in 1995, Pratt actually eliminated that by attaching an elastic element between the gearbox and the part of the robot that interacts with the environment, the output. What we found with this is by attaching either a spring or a rubber band or some elastic component, you can eliminate the reflected inertia from the system. However, with this, you have a fixed compliance because that elastic element, you only have control of it at the design level. So that's not very good, and ideally you would want to be able to control the characteristics of that elastic component throughout the entire time of using your actuator. So from there, people looked into how we can achieve variable stiffness in actuators, control over these inertial or these impedance components. So initially, people looked at how we can take inspiration from the human body in bio-inspired design. So this is something very similar as our biceps and triceps. If I told you, if you wanted to stiffen your elbow, what would you do? You would probably contract both your bicep and tricep. By using these two muscles, or these two motors in this case, we can control not only the output link angle, but we can control the second degree of freedom, which is the stiffness. But with this, since we're taking inspiration, we have these two muscles or two motors, you're increasing the complexity of the system with the addition of the second motor, essentially having two motors so you can control position as well as stiffness. On the other side, if we don't look at inspiration from human body, we can look at non-bio-inspired designs, which use two motors for the 2 degrees of freedom, but they're completely independent, where one motor is specifically looking at controlling position, and one motor is specifically looking at controlling stiffness. For example, with this, if you had this long arm here that has a motor to control the angle, you could then control where the bending point is using a separate motor, to where if the pivot point is on top of the force point, well, if you try to move a pivot, nothing's going to happen. You would essentially have infinite stiffness. Whereas if the pivot point moved all the way to the spring point, you would have essentially 0 stiffness. And something like this, again, since it requires 2 motors, it starts to add a lot of complexity and a lot of bulkiness to the system, to where this is something we have upstairs, this treadmill with adjustable stiffness that uses the same principle. And you can see it takes up quite a lot of space, not able to be made in a portable form factor for the desired applications that we would want with physical human-robot interactions. So what can we do then? Well, we can look at viscoelastic polymers. And this is, again, where we revisit the kitchen for something that might be familiar to us. Something such as, in this case, a scrub daddy, which is a sponge made out of a material called polycaprolactone. And if you're familiar with this at all, this material, polycaprolactone, as you increase the temperature and get it hot, it becomes very compliant. And if you get it cold, it becomes very stiff. With this, we have direct control over those mechanical properties that we desire using temperature rather than an additional motor. So now we can control it without any additional moving parts, and we can hopefully decrease the form factor and decrease the size based on just using temperature with the flexible peltiers we mentioned before. So with this, with viscoelastic polymers or anything that's viscoelastic, we have 2 key characteristics that are time dependent, and that's in creep and stress relaxation. With a viscoelastic material, if you apply a constant stress, you'll experience creep, which is while the stress is held constant, your strain actually increases. And then with stress relaxation, if you do the opposite, if you maintain a constant strain, the stress actually decreases or relaxes. And with this, we look at the polycaprolactone and we look at some of the compression characteristics with temperature. So here we see as we increase the temperature, we're able to get much more compression with a similar weight. With this, we can then verify that by making a design that utilizes this material at a joint. So what we do here is we implement a variable impedance module between our motor and gearbox and output link. And what we're putting in between is a fixed compliant component similar to the series elastic actuator we saw previous, as well as this viscoelastic polymer in which we control stiffness and damping factors based on the temperature. And we make that design, and something I want to point out is on the right side here, we have this inner rotor, and this wheel that we have in the middle is what's connecting the output link to the gearbox. So it's connected through 2 things. It's connected by coming into contact with fixed springs, sort of like a series elastic actuator, as well as with that viscoelastic polymer, that polycaprolactone. So as the joint is moving, the polycaprolactone is being compressed, and whatever characteristics it has based on the temperature are being transferred to the output limit, or however the length of the joint is interacting with the environment. So with this, we did tests of attaching it to a motor and having it driven by a certain signal, and we were able to verify that as the temperature increases, not only does the stiffness decrease and the joint become more compliant, but we can also see damping decrease. Now, something to point out here is as the temperature increases, the stiffness almost becomes negligible, to where the only stiffness associated with the joint is that of the fixed spring component. So then it becomes much more reliant on the damping or the viscous properties as the temperature increases. So we had it follow a sinusoidal trajectory and we looked at how the output link angle changed based on what we were driving it with the motor, and that's how we were able to achieve this system identification, or understanding how those mechanical properties of the viscoelastic polymer change with temperature. But we see an issue with this. When we have this inner wheel and this rotor come in contact with the polycaprolactone, we compress it. And if you compress it and then return to an initial position, the material itself stays compressed. So you get this loss of contact between the polycaprolactone and your rotor blade. This loss of contact, or backlash in this case, is very undesirable from the stance of implementing variable impedance actuators into actual applications. You traditionally want a lot of predictability and control of how your joint is going to react to any kind of perturbation or any kind of signal beforehand. And due to the viscoelastic characteristics that are time dependent, such as the stress, relaxation, and the creep, you have this drawback here. So from here, we pivoted and we looked at how we can change the design to not rely on compression, but to instead rely on shear forces. So what we did here is we changed the rotor blade where instead of compressing, we are actually just shearing over and having these shear forces between the rotor blade and the polycaprolactone. And what you'll notice the difference between these two is that here you experience this loss of contact, whereas here you don't experience loss of contact at all, as well as you decrease the amount of space that the heat needs to travel through the polycaprolactone. So this vertical area here, you're able to heat quite efficiently just based on decreasing the amount of space that the polycaprolactone has while eliminating that backlash. So we did the compression tests before. This time we did shear tests with rheology of the polycaprolactone. Initially, what we did is we did an amplitude sweep to verify, typically with viscoelastic materials, you have this linear viscoelastic region. Once we verified that, we conducted frequency sweep, and something we saw with this that's undesirable for variable impedance actuators is, again, when it comes to a joint, you might have a bunch of different kinds of perturbations that interact with it. If you think of your elbow, maybe you bump into someone in the hallway, maybe you use it to open a door, having different speeds that those interactions take place. Well, what we find with this frequency sweep is that at lower frequencies, at perturbations that take a lot longer time, we have primarily viscous response, so a lot more damping behavior. And then at higher frequencies, around about 100 hertz, you have primarily the elastic response, or elastic characteristics of the polycaprolactone. From here, we did tests on the creep and stress relaxation, and we saw with these that the material, as the temperature increases, it starts to show more of those viscoelastic properties, or those viscoelastic characteristics, which again, in this case, because they're time dependent, it's not very desirable for our joint. If we have a joint that is maybe supposed to, let's say for an elbow, that's supposed to flex 5 times, we don't want it to where each one of those 5 times it has a different response or a different level of compliance. We would ideally want it to be not dependent on temperature. So we make a different design with this, and with this, the interactions between the inner rotor and the compliant components is what we want to focus on. So it's a little hard to see here. I'll show you this model we have where the rotor is actually going to come in contact with 4 different torsion springs, and these torsion springs are similar to the series elastic actuators we looked at previously, where they have a fixed compliance. And at that point where they come in contact, we can actually understand the force response. But then for the polycaprolactone, now we're not working with compression. We would instead have to look at the side view of this same rotor. And this arc that you see here is actually the polycaprolactone itself, to where we can look at the shear forces associated with that, to where we can directly heat the polycaprolactone and then record the shear response of the or we can record the same angles we did previously, but this time to characterize the shear characteristics of polycaprolactone. So with that, we take a look at an output link. And what we did is we started at low temperatures, and if we had an output link like this, we just deflected it to a certain angle and then let go and recorded the response back to that equilibrium point. What we found is at low temperatures, we had a very stiff joint. We were able to calculate the stiffness. And then as the temperature increased, you had much more compliance in the joint, where you can see things such as the overshoot increase as well as the oscillation. And then finally, we took it a step further and increased to 100 degrees, and we saw even lower stiffness with this. So with this new shear design that we enabled, we primarily looked at the module itself, so we didn't have a motor driving it, we just perturbed the output link. In the future, we will have to attach a motor to it and fully characterize it and see what kind of not only stiffness, but also damping behavior it has as temperature increases. So with this, we have two main areas that we took a look at today. The first area being soft robotics, where we look at the agonist-antagonist designs, essentially having a Peltier, but taking use of both sides of the Peltier, being able to fully use both sides, as well as have that reversibility using the active heating and active cooling. And we saw that that has its own considerations in itself with the effects of gravity and whatnot, but we also saw benefits when it comes to the speed and when it comes to different designs that are more bio-inspired. When it comes to the variable impedance actuator, traditionally, when it comes to the impedance control, it's just been mechanically controlled. It's been primarily looking at how can we add a motor and have that motor control that second degree of freedom, that stiffness or impedance. With this is the first time that using temperature to control the mechanical properties of a material has been fully realized for an application such as this. And in the future, we really want to look at, for the soft actuators, what can we do to enhance the performance? We don't really want a locomotion like I showed you before, to where it takes a step and then has to wait, and then takes a step and then has to wait. We would ideally want to have a good enough transient response to where we can continuously use it for a much longer amount of time. So with this, there's much more that needs to be done with temperature tracking, as well as enabling hysteresis for the heating. So essentially having it to where the Joule heating and the thermal conductance don't have as much of an effect over time. And when it comes to the VIA and the joints, this is where currently, when it comes to controlling the impedance and in controlling the stiffness with temperature, it takes a relatively long time. In applications that utilize motors, they're able to change stiffness very quickly. And ideally, we move it more towards that online implementation rather than offline implementation that we've looked at today. With that, for the shear mode design, we did see enhanced performance because we eliminate that backlash associated with the compression, but we still need to implement a direct drive motor to fully characterize the damping properties as well, the polycaprolactone. Finally, with this, I do want to say that all the work I talked about today is available online at somewhere. We also patented both of these projects and these designs. And then finally, I want to acknowledge my committee members for being here. Dr. Zhao, I know, is on Zoom. I would not have gotten anywhere close to where I am today doing research without input from each of you, as well as all the contributors that have been in the lab. My family, my friends. I think that having a good support system going through a PhD is very important, and the wonderful staff that has responded very quickly to emails of me asking to put orders in have been undeniably helpful. Even anyone that just had a conversation with me as I've been working on the research. As well as I want to acknowledge the two funding sources for these projects, the first being my NIH GRISE Fellowship through the College of Science. It has allowed me to focus purely on research, which has helped a lot in the productivity throughout this time, as well as Dr. Jafari's NSF Career Award, which has supported the first project working with thermoactive soft actuators. And maybe next time you're in your kitchen, you will take a look around and discover what is going to enable the robots of tomorrow.
Questions?
Trevor?
Yes.
So, in the big scheme of things, in the big picture, where do you see these the two things that you discovered? Where do they fit in to create a comprehensive robotic solution?
So great question. So for all kinds of soft robotics and all kinds of variable impedance actuators, soft robotics, each one has their drawbacks of the different stimulus. Hopefully with the work I've done, we get a little closer to implementing them into things such as prosthetics or wearable or rehabilitative devices. When it comes to the joints, the variable impedance actuators, currently we see a lot of implementation in just any kind of lab diagnostic setting that is working with humans, such as the treadmill with adjustable stiffness we have, as well as any kind of sort of exoskeletons or something that primarily focuses more on joints and having compliance with interacting with the environment. So I think that as we see robotic platforms more integrated into everyday life, maybe not a Roomba or anything, we will probably see a lot more breakthroughs in technologies such as this and inching it forward so that we can have systems that are actually implemented.
So currently, there's like humanoid robots. They're Unitree has just come out with one, and then of course Musk's Tesla as well. So have you seen these concepts being incorporated into your humanoid robots? Because they're being used for industrial applications, lifting weights in factories and things like that.
So that's a great point because humanoid robots are like a very, there's a lot of hype around them right now. What I'll say is with them and as well as with quadruped robots such as the Spot, the dog we have upstairs, a lot of the time, since this technology isn't there yet, they implement active impedance control, which is all controlled through software and sensors, which what that does is it makes it a lot more expensive. Like everything you saw today is relatively cheap. With that, it makes it a lot more expensive as well as increases that complexity, and it makes it to where each one has to be very over-engineered. So like the videos you see of the humanoid robots performing certain tasks, they've probably gone through that task a million times. And the engineers have made sure that like, oh, the force sensors are coming into contact in the right area, or there's not too much current going through a joint motor. With this would ideally make it to where the applications themselves, you can just attach the technology, and then there's a lot less engineering that has to go into it, where it can already, just due to the inherent material properties, interact with more unknown environments better.
The last question.
Yes.
Is the repeatability of actions of these things. Because in the ultimate solution, these things have to be implemented to help human beings improve quality of life. They have to be repeatable over a wide range of conditions. Right? What kind of findings did you get from your studies of repeatability and reliability?
Yes, so what I'll say is when it comes to the thermal domain or heat domain, it's relatively unpopular in the grand scheme of soft robotics because it's slow. Because if you're wanting to implement it to where you have a prosthetic device driven by this, you don't want it to take 5 minutes for someone to open the door and then another 5 to close it. With that, the flexible peltiers that we've introduced to these systems, they have a lot of promise when it comes to enabling more repeatability or faster speeds. However, the thermal domain is very complex and there's a lot more optimization that needs to go into like the heat transfer and thermodynamics behind it all. But as materials and as even like the Peltiers themselves improve, I'm sure we will see many more breakthroughs and getting closer to the ideal case.
Questions?
Yes.
So very nice job. I have two questions regarding the first page. You showed the previous study, not from you, basically using PDMS after the phase separation and use the IPA to expand so that can move stuff. Have you had an idea like what's the lifetime for this kind of modulator? Think about PDMS is kind of like a gas permeable. So over time, IPA particularly when you heat it up, IPA may diffuse out.
Yeah, so something they don't, I'll see if I can come back to that. Something I don't show, or they didn't show in the video, is that exactly. Whenever you have that phase change composite, you may only have a good 5 or 6 actuation cycles before you actually have to rejuvenate the phase change fluid. So in this, what you'll see is if you ran this video for another 10 minutes, it would eventually stop actuating. And that's because it leaks out. With that, some rejuvenating it essentially consists of just dipping this in the phase change fluid, so you can imagine it takes a lot more to really have that retention. What we found with the pouch motors is that the initial one I made, I think, was like 1.5 years ago, and it still actuates now, even after multiple cycles. So that the new technology that we're looking at, it's more dependent on the life cycle of the film than the material, the phase change fluid inside.
So actually, my second question is about the pouch modulator. If you go to the movie, the locomotion.
Oh, yes.
Yeah. So this one, my understanding is that the flexibility, dimensionality, and the speed of this locomotion depends on the design of each compartments of this pouch. Have you thought about like using another way, for example, a cap to design regarding the size of each compartment? Because if you think about if the whole pouch motor just have one compartment, then its movement different from that has 10, right? So have you thought about that?
Yes, so what we find is that whenever, like let's say you have a Peltier such as this is 40 millimeters by 40 millimeters, if you just have one central cavity, what you'll find is there's a lot of buckling that's just inherent to the mechanical properties of it. Now, we have kept it relatively simple in the channel design or in the geometry, just due to being able to model it, but we didn't look extensively. What we did find is that as you increase the number, like what you'll see on this top one, we really only have these 3 cavities, but we could have it to where the rest of this is all cavities. It really just comes down to wanting to centralize the fluid displacement due to gravity just on top of the Peltier. If we increase it more, it might have a lot more significant curvature during actuation, but then it would slow down because now you have no assurance that when it returns to liquid form that it will pool here. It could pool anywhere down below.
Very nice work. The question that I have, non-engineer here, the temperature dissipated to cool down seems to be a challenge. Have you looked at maybe using other ways other than just the ambient temperature to have that effect and cool down so that it can decrease that time period? So anything, and even the increase, so chemical reactions might be potential. So using catalysts to be able to either heat or cool down that sort of aspect. And then my second follow-up question is, the energy to produce the temperature, is this something that a battery could be able to produce? And so it's something that's applicable in terms of being able to move these apparatuses around and not require, plugging in somewhere.
So great question. To answer the first, we haven't looked into catalysts specifically, but we've looked into things such as like a fan or some sort of active airflow, as well as there's a lot of research going into like keeping these technologies submerged so that the liquid, like just water, can cool it off faster. That isn't something we necessarily focus on, but that is where the primary focus is in the field, just because there's going to be a bottleneck eventually when it comes to just running current through. To answer the second question, all the videos I showed you today are 1 amp, 5 watts, so it's very, very manageable with the battery. And one of the next steps is to actually make it completely untethered where it can carry its power supply as it moves.
May I ask you a question for the professor? Is there any reaction that we can do reversible several times without really?
Yeah, that's what I was trying to think about. I'll think about it.
But yeah, I mean, when something like that is focused on, I will say that this will sort of skyrocket forward.
So I'm thinking like, if there are any you guys in the field, so given there's some kind of materials, when you provide the stimuli, which may induce the phase change and lower temperature. So when you touch that one with the approach modulator, maybe you can control heating and cooling and speed up the whole motion.
Yeah, exactly. So like something that people have done is instead of just a traditional heat sink that's made out of aluminum, people have made phase change heat sinks that are made out of like a paraffin wax that have maybe copper powder inside, so that you can ensure that the temperature moving into it or the heat moving into it is enhanced, as well as since you have that phase change occurring, it's not increasing the temperature further, and the closer the two temperatures of the Peltier are to each other, the more efficient the device will be. So.
But that has a speed.
Yes, yes.
Yes, sir.
Great. Well, I believe at this point we'll be doing the private portion. So I thank everyone for being here. We have to sort of walk across A1